In this video, we're going to be talking about how to find limits analytically, but by algebraic manipulation. So limits can be found using direct substitution, but what happens when that doesn't produce an answer? So let's take a look at an example of that. If we have the limit as x approaches -2 of x plus 2 over x squared minus 4. Let's say we try direct substitution. That's always your first attempt when you're doing a limit problem. Always try direct substitution as your first line of defense here. And we're going to plug -2 in, and I get 0 over 0. So 0 over 0, and if another problem produces infinity over infinity, that would be a similar idea too. This is considered indeterminate, okay? It does not mean that the limit is 0. It does not mean that the limit does not exist. It just means from this method, we cannot determine the answer, and we have to really think about this as do more work. Okay, I have to find another way to get my answer. So we want to interpret indeterminate 0 over 0 as do more work. So we can evaluate these limits again after some algebraic manipulation. So you might notice that denominator here, x squared minus 4, is something that we can factor, right? That's the difference of two squares. So let's say I do factor it. I'd have x plus 2 and x minus 2 in the denominator. And notice these x plus 2's here are canceling out, because basically when I say cancel out, they equal 1, right? Anything over itself is 1. Now if I simplify that, I get 1 over x minus 2. If I plug -2 into that, now I actually get an answer. And you can see that I get -1/4 as my answer here. Let's take a look at another one. I have the limit as x approaches 36 of x minus 36 over radical x minus 6. Just like the previous example, this would produce an indeterminate answer after direct substitution. So we'll have to algebraically manipulate the expression. Okay, and you can see here I've plugged in 36 for each x value, and I got 0 over 0, indeterminate. Once again, I just want to remind you, 0 over 0, the biggest misconception is that means that the limit is 0 or that it doesn't exist. That is not true. That means we need to do more work to determine the answer. So I can do this by rationalizing the denominator, basically getting the radical out of the denominator here. So if I have x minus 36 over radical x minus 6, what I'm going to do is I'm going to multiply the numerator and denominator by an equivalent of 1, but I'm going to multiply it by the conjugate of what is already in the denominator. So since this was radical x minus 6, notice the minus, I'm going to now multiply by radical x plus 6. Okay, and you'll see why this works in a second. When I have the numerator here, don't actually distribute this. So when I have this here, I'm just going to leave it exactly as is, but I am going to distribute the bottom, okay, because the bottom is really what we're trying to clean up here. So radical x times radical x is just x. If I think about this as multiplying these two binomials, I'm going to get plus 6 radical x. So think about it like this. So x plus 6 radical x minus 6 radical x minus 36. And these terms equal 0, so we're going to cross those out. So now my denominator is a lot cleaner. It's x minus 36. And you can see in this next piece here that it cancels out, just like the previous problem, with a term from the numerator. So really what I'm left with is radical x plus 6. Now resubstitute, okay? So once you've simplified, you're going to resubstitute into your new expression, and here we have an answer. So radical 36 plus 6 gives us 12. So in summary, try to evaluate a limit first by direct substitution. If your answer is indeterminate, then we're going to try algebraic manipulation. All right, let's take a look at some practice problems. All right, number 1, the limit as x approaches -3 of x squared minus 9 over x plus 3. All right, let's say we start by our first method. I don't like to skip this because I want us to remember that direct substitution should always come first. But you can see here that I'm going to get 9 minus 9 over -3 plus 3, which is 0 over 0, or indeterminate. So I'm going to rewrite my original expression by factoring the numerator and denominator. Just the numerator actually in this case, sorry about that. So just the numerator, and I'm going to see that these x plus 3's we can get rid of. So this is equivalent to the limit as x approaches -3 of x minus 3. Now let's resubstitute in. So -3 minus 3, and we get an answer of -6. Number 2, the limit as x approaches 6 of x minus 6 over 3x squared minus 17x minus 6. All right, so we are going to substitute first. And when we do this here, we are going to get 0 over 0, which is indeterminate. All right, after that, we are going to think about, well, how can I factor here? So in the previous problem, we were able to factor the numerator. In this one, we can factor the denominator. So just a side little lesson in factoring here. I'm just going to do this kind of boxed off in the corner. I have 3x squared minus 17x minus 6. You can jump right to factoring if you want, okay? And you might know, okay, 3x is going to go in front of one parentheses, x in the other. That's fine. Or you could think about this as I'm going to do factor by grouping. That's the method I'm going to choose. So when I do that, I'm going to multiply the a and c terms, and I get -18 when I do that. So I'm looking for numbers that add to -17, but multiply to -18. Okay, and I can think about those numbers as being -18 and +1. So what we're going to do is, using those two numbers that we just came up with, I'm just going to rewrite the original expression, but expand upon that -17x. Once I have that, we're going to look at the first two terms, the 3x squared minus 18x, and factor using a GCF, or greatest common factor. So that is going to give me 3x times x minus 6. Over here, the GCF would just be 1 times x minus 6. When doing factor by grouping, if you do it correctly, what's in these parentheses should always match, basically, should be equal. And when I group, I have 3x plus 1 times x minus 6 as my answer here. All right, now that I'm going to factor my denominator of the original problem, or now that I have the factors, I'm going to rewrite this. And you're going to see these x minus 6's go away. And so this is equal to the limit as x approaches 6 of 1 over 3x plus 1. Be careful that you put 1 in that numerator as a placeholder. And now let's resubstitute in. So 1 over 3 times 6 plus 1. And we're going to get 1 over 19 as our answer. Okay, for number 3, we have the limit as x approaches 4 of x cubed minus 64 over x minus 4. Let's try our direct substitution. And we get 0 over 0, indeterminate. And then just like before, we are going to now rewrite this using some algebraic manipulation. So this is equal to the limit as x approaches 4 over. Denominator we're going to leave alone. The numerator we're going to factor out in x minus 4, and that will leave us with x squared plus 4x plus 16. That's because we have a difference of 2 cubes in the numerator. All right, let's get rid of these x minus 4's. And now let's resubstitute in. So I have 4 squared plus 4 times 4 plus 16. So this will give us 16 plus 16 plus 16, which will give us 48. Number 4, the limit as x approaches 9 of x minus 9 over radical x minus 3. This looks similar to the question we saw on the first page. We'll start with our direct substitution, of course, and we will get 0 over 0 indeterminate. So we are going to rewrite this using some algebraic manipulation. And the method we're going to use here is by multiplying both the numerator and the denominator by the conjugate of the denominator. So I am going to leave the numerator alone, so it's just x minus 9 times radical x plus 3. The denominator, when I multiply and distribute that out, will give me x minus 9, and that's the goal because we want these to basically go away. So we have the limit as x approaches 9 of radical x plus 3. Now let's resubstitute, so radical 9 plus 3, or we get 6 as our answer. Okay, for number 5 here, the limit as x approaches 8 of radical x plus 1 minus 3 over x minus 8. All right, let's start with our direct substitution, of course. And you will see, of course, we are going to get 0 over 0 indeterminate. All right, from here, we have to think about how can we rewrite this. So think about this compared to the previous problem. In the previous problem, the denominator had the radical in it. In this problem, the numerator has the radical in it. Okay, so think about how we're going to work with that in terms of conjugates. So I'm going to rewrite this original expression. But what I'm now going to do is I'm going to multiply it, top and bottom, just so it's the equivalent of multiplying by 1, by the conjugate of the numerator. Okay, now let's multiply this out. In the numerator, when I multiply this, radical x plus 1 times radical x plus 1 is just going to be x plus 1. The negative 3 times positive 3 is going to be minus 9. Keep in mind here that if you use FOIL, those inner and outer terms are going to cancel each other out. The denominator, I'm going to leave it. I'm not going to actually multiply here. Let's rewrite this again, because now my numerator can be quickly simplified to x minus 8. And we can see where our simplification is going to come into play. So this is the limit as x approaches 8 of 1 over radical x plus 1 plus 3. Now let's substitute, now that we've simplified. And we're going to get 1 over basically 3 plus 3, or 1 over 6. All right, one last example here. This one looks a little bit different than the other ones that we have seen. So it's the limit as x approaches 0 of 1 over x plus 2 minus 1/2 over x. So we have a complex fraction going on here, a fraction in a fraction. We'll start by doing our direct substitution, and we will see that we are going to get 0 over 0, right? That numerator is 1/2 minus 1/2. The denominator is simply 0. All right, so what we're going to do is I'll do this off to the side for a second, just as like a little bit of workspace over here. We need to work with this 1 over x plus 2 minus 1/2. The thing we could do here to simplify this is get common denominators. So I'm going to multiply this first fraction by 2 over 2, and I'm going to multiply this fraction by x plus 2 over x plus 2. Okay, the reason that this is going to work is because now the denominators are going to be the same. I'm going to keep that in parentheses for a second. And that will help us simplify a little bit as we go through the problem, okay? All right, so now what I'm going to do is I'm going to merge that into one single fraction. So 2 minus x minus 2, right? We have to distribute that negative across over 2 times x plus 2. The numerator is going to simplify a bit. So all of this comes out to be negative x over 2 times x plus 2. Now let's take that and bring that back into our limit that we were working with originally. By the way, if you did want to distribute the 2 times x plus 2, you could here. All right, so what I did here, I'm going to highlight this and then I'll erase that in a second, is we basically took that numerator and we simplified it by getting common denominators. Here's why that helps us, because now that I have a single fraction in the numerator, I could divide these two out here, or think about it if you've learned keep, change, flip before. And you can see we got some more simplification going on. So we have the limit as x approaches 0 of -1 over 2 times x plus 2. And we are going to now resubstitute. So we have -1 over 2 times 2 basically. So -1/4 as our answer here.